Hi, and welcome back to Module 3. This is Section 8. In this section, we're going to take a look at how you can tune the model's hyperparameters to improve model performance. Recall from an earlier module that hyperparameters can be thought of as the knobs that tune the machine learning algorithm to improve its performance. Now that we're looking more explicitly at tuning models, it's time to look more specifically at the different types of hyperparameters and how to perform hyperparameter optimization. There are a couple of different categories of hyperparameters. The first kind are model hyperparameters. They help define the model itself. As an example, consider a neural network for a computer vision problem. For this case, additional attributes of the architecture need to be defined, like filter size, pooling, and the stride or padding. The second kind are optimizer hyperparameters. They relate to how the model learns patterns based on data, and they're used for a neural network model. These types of hyperparameters include optimizers like gradient descent and stochastic gradient descent. They can also include optimizers that use momentum, like atom, or that initialize the parameter weights with methods like Xavier initialization or He initialization. The third kind are data hyperparameters. They relate to the attributes of the data itself. These include attributes that define different data augmentation techniques, like cropping or resizing for image-related problems. They're often used when you don't have enough data or enough variation in your data. Tuning hyperparameters can be very labor-intensive. Traditionally, this was done manually by someone who had domain experience related to the hyperparameter and the use case. This person would manually select the hyperparameters based on their intuition and experience. Then they would train the model and score it on the validation data. This process would be repeated over and over again until they achieved satisfactory results. This manual process isn't always the most thorough and efficient way of tuning hyperparameters. With SageMaker, you can perform automated hyperparameter tuning with Amazon SageMaker Automatic Model Tuning. It finds the best version of a model by running multiple training jobs on your dataset by using the algorithm and hyperparameter ranges you specify. It then chooses the hyperparameter values that results in a model that performs the best as measured by a metric you choose. It uses Gaussian process regression to predict which hyperparameter values might be most effective at improving fit. It also uses Bayesian optimization to balance exploring the hyperparameter space and exploiting specific hyperparameter values when appropriate. And importantly, automatic model tuning can be used with built-in algorithms from SageMaker, pre-built deep learning frameworks, and bring your own algorithm containers. Suppose that you want to solve a binary classification problem on a fraud dataset. Your goal is to maximize the area under the AUC curve metric of the algorithm by training a linear learner algorithm model. You don't know which values of the learning rate, beta 1, beta 2, and epochs you should use to train the best model. To find the best values for these hyperparameters, you can specify ranges of values that SageMaker hyperparameter tuning will then search. It will find the combination of values that results in the training job that performs the best, as measured by the objective metric that you chose. In the example, SageMaker hyperparameter tuning launches training jobs that use hyperparameter values in the ranges you specified, and then returns the training job with the highest AUC. Hyperparameter tuning might not necessarily improve your model. It's an advanced tool for building machine solutions. As such, it should be considered part of the scientific method process. When you build complex machine learning systems, like deep learning neural networks, exploring all possible combinations is impractical. To improve optimization, use the following guidelines when you create hyperparameters. First, instead of using all hyperparameters, limit the number of hyperparameters to the ones you think would give you good results. The range of values for the hyperparameters you choose to search can significantly affect the success of hyperparameter optimization. Although you might want to specify a large range that covers every possible value for a hyperparameter, you'll get better results by limiting your search to a small range of values. If you get the best metric values within a part of a range, consider limiting the range to only that part. During hyperparameter tuning, SageMaker attempts to figure out if your hyperparameters are log-scaled or linear-scaled. Initially, it assumes that hyperparameters are linear-scaled. If they should be log-scaled, it might take time for SageMaker to discover that on its own. If you know that a hyperparameter should be log-scaled and you can convert it yourself, doing so can improve hyperparameter optimization. Running more hyperparameter tuning jobs concurrently gets more work done quickly, but a tuning job improves only through successive rounds of experiments. Typically, running one training job at a time achieves the best results with the least amount of compute time. Say that you have a distributed training job that runs on multiple instances. In this case, hyperparameter tuning uses the last reported objective metric from all instances of that training job as the value of the objective metric for that training job. Design distributed training jobs so that they report the objective metric you want. Now that you've gone through the end-to-end process of training and tuning a machine learning model, it's worth talking about Amazon SageMaker Autopilot. This service can help you find a good model with little effort or input on your part. With Autopilot, you create a job that supplies the test, training, and target. Autopilot will analyze the data, select appropriate features, and then train and tune the models. It will document the metrics and find the best model based on the provided data. The results include the winning model and metrics and a Jupyter notebook you can use to investigate the results. Although using Autopilot doesn't remove your need to pre-process the data, it can save you time during feature selection and model tuning. Some key takeaways from this section of the module include these points. First, model tuning is important for finding the best solution to your business problem. Hyperparameters can be tuned for the model, optimizer, and data. SageMaker can perform automatic hyperparameter tuning. And finally, overall model development can be accelerated by using Autopilot. That's it for this video. See you in the next one.
Once you have data ready to train a model, you will iterate several times to tune the model's hyperparameters in an attempt to get the best results. This can be a tedious process to do by hand. Fortunately, Amazon SageMaker provides a hyperparameter tuning job that you can use to remove the heavy lifting. Tuning can be a repetitive task, so it's worth learning the code to be able to do this. We'll also look at the console output once our job's running. Now, before we get started, let's take a look at the data we're going to use to train our model. Once again, I'm using the wine quality dataset from UCI data repository. If we import that in, we'll do a little bit of pre-processing and then take a look at the data. The first column you can see is the quality column, and this is actually our target. You'll notice the code here actually creates a mapping. So we're mapping the actual quality values down to a number between 0 and 5. The rest of the columns are just various attributes of wine, citric acid, chlorides, alcohol level, that type of thing. Next up, we're going to split the data. We're going to use sklearn to split the data, and we're going to split the data into 3 different sets. We're going to take 80% for the training set and 10% each for the test and the validate set. We're going to make sure that we have a balanced data set by specifying the stratify for the quality column. Next up, we want to upload this data to S3 so we can actually use them in the model. And finally, we'll go create the estimator that we can use to then tune the model. There's nothing special about this estimator. It's actually the estimator we've borrowed from a previous demo. You'll notice that we're actually specifying hyperparameters here, but we're only specifying really the number class, which is how many classes for the model to try and determine. In this case, it's 6, which matches the number of different values for our quality column. Next up, we create the input channels. This is basically telling SageMaker where the data is. So we've got a training channel which points to the training data and a validate channel that points to the validation data. The validation data is used to calculate the metric which will be used to evaluate the model. Now we're going to create the hyperparameter tuning job. There's a couple of things to note here. First of all, this is the hyperparameters that we're actually going to choose. And you're probably wondering where we got these from. If you take a look into the documentation on tuning an XGBoost model, you'll see there's two important sections. The first one is the metrics that are computed by the XGBoost algorithm. When tuning the model, we have to choose one of these metrics as the objective to evaluate the model. Which objective you choose is really going to depend upon the type of machine learning problem you're trying to solve. Next up are the tunable XGBoost hyperparameters. Here's a list of the hyperparameters that you can tune, as well as some recommended ranges. But also note the hyperparameters that have the greatest effect on the XGBoost objective metrics are the alpha, the min child weight, subsample, ETA, and numRound. And this is why in our example, we've selected these hyperparameters to tune. The objective metric we're choosing is the validation M error, and we're going to try and minimize that. As reference, the M error is the multi-class classification rate calculated as the number of wrong cases divided by all cases. We need to specify the maximum number of jobs, in this case 40, and then how many parallel jobs we want to run. Since this is going to tune the model based upon the results of the previous job, leaving it as 1 is probably not a bad idea. If we run this, it's going to run up to 40 training jobs to try and find the best one. As you can imagine, this is going to take a little bit of time. So let's come back when that's complete. The job's almost complete, so let's switch across to the console. You can see our job's now complete, and it took around 2 hours to complete the 40 training jobs. If we click into the job, we can see all of the different training jobs that have been executed. Here's the last 10, but we can go change and view all 40. You can see the objective metric value changes between each of the models. Remember, this is the metric that the model's trying to get the best value for. We can find the best training job through the best training job tab. And this is the best training job here with the M error value of 0.28 or 28%. And here's the best hyperparameters that were used in this particular job. If we flip back to our notebook, we can do the same type of thing through a little bit of code. Here what we're going to do is query the hyperparameter tuning job analytics, and this should give us a data frame with all of the training job results in. To find out the best, we can actually go look for the best training job, and then if we want to create a model for that job, we can simply attach an estimator to the best training job. We could then use that to create a batch transformer or deploy an endpoint. That's it for this demo. We'll see you in the next one. In this demo, we're going to see how Amazon SageMaker Autopilot can help you accelerate your machine learning projects. You've probably realized by now that machine learning is a lot of experimentation with different features, parameters, and models. Let's see how Autopilot can help with this. Autopilot can be launched from the API or from Amazon SageMaker Studio as an experiment. If you haven't seen SageMaker Studio yet, it's built on Jupyter Lab, so much is going to be familiar. Before we get started, let's look at the problem we're going to try and solve. A typical introductory task in machine learning is one that uses a dataset to predict whether a customer will enroll for a term deposit at a bank after one or more phone calls. For this task, we're going to use the bank marketing dataset available from the UCI database repository. Direct marketing through mail, email, phone, etc. is a common tactic to acquire customers. Because resources and a customer's attention are limited, the goal is to only target the subset of prospects who are likely to engage with a specific offer. Predicting those potential customers based on readily available information like demographics, past interactions, and environmental factors is a common machine learning problem. Before we start the experiment, let's take a look at the data. I'm here at my notebook and I've got the usual imports, and we're going to download the data set from S3 and take a look at the data. You can see I've got some information about job, age, marital status, and so on. And the final column is Y, which is our target variable. Now, I really don't have to do anything with the data. I could actually start an experiment now. But one thing you might want to do is just hold back some data for validation and testing later. So what I'm going to do is use train test split to create two data frames, one containing 95% of the data, which will be our training set. The other will be 5% for testing. And we'll go upload those back into S3 as so. One thing to note, when we convert the data frame back to a CSV, we're actually going to include the header. Now, typically, you would remove the header for a machine learning data set, but in the case of Autopilot, we can leave the header in there. Let's create a new experiment. There isn't too much to specify here, just the job name, an output location, and where to find the data. So let's give the experiment a name. We'll select our MLF demos folder and pick our bank training dataset. The target variable, if you remember, was Y, and we need to specify an output location. We can also select the type of machine learning problem. We can leave it on auto, or we could select one of the other options. Finally, do we want to run a complete experiment or just create a notebook with the candidate definitions? We're going to create the full experiment here. With the experiment created, there's nothing to do for the next 5 to 10 minutes, so let's pop back then. Once the analyzing data phase is complete, there are a couple of notebooks generated. The first shows some basic information about the data. This notebook contains some of the data and statistics a data scientist would look at. There are some suggestions in the blue highlighted boxes which you should look into. This dataset is pretty clean with little errors, so there isn't much for us to do, but you should look through it anyway. We can see that there are 39,128 rows from the training dataset. The dataset has 21 columns, and the column named Y is used as the target column. This is identified as a binary classification problem. Here are two examples of the labels no and yes. If we scroll through the notebook, we get some typical output you might see in any type of notebook. Here we have the data, we've got some column analysis, percent missing values, some statistics, some descriptive statistics, and so on. This notebook contains the commands that are used to run the SageMaker Autopilot workflow. We can look through this notebook to get some insights about the data, but also how Autopilot is processing the data, training the model, and tuning the hyperparameters. Again, you can see the database, 21 columns, column name Y is the target, and so on. There are some blue highlighted boxes with some recommendations that you can follow too. You You can see that Amazon SageMaker Autopilot has analyzed the dataset and generated 10 machine learning pipelines that use 2 algorithms. The first pipeline is using an XGBoost as the model, and it's transforming the data through a robust imputer, converting missing values to NaN. A categorical features are converted using a threshold 1-hot encoder, and it merges all the generated features together using a robust standard scaler. The next model is very similar, instead using a robust imputer, not converting missing values to NaN, and the rest is the same. We've got a linear learner model, not using XGBoost. We have another XGBoost model, and so on and so forth. Autopilot uses a multi-algorithm hyperparameter tuning job to tune the candidates using typical recommended parameter ranges for the 2 algorithms selected, in this case XGBoost and linear learner. Once the tuning jobs are complete, you can then select the best model and deploy like you would any other model. With the analyzing data and feature engineering stages complete, we're now onto model tuning. You can see that the training jobs are now being run. Again, we just want to wait until this is complete, so we'll drop back in later. Once the autopilot experiment is complete, you'll be able to select the winning model and deploy it from Studio. You can also use the model to perform a batch transformation on any data that you held back. In this demo, you saw how with very little input, Amazon SageMaker Autopilot can analyze your data and train and tune a model. This might not be the best model possible, but it will give you something to work from. That's it for this demo. We'll see you in the next one.
It's now time to review the module and wrap up with a knowledge check. In this module, you learned how to formulate a problem from a business request, obtain and secure data for machine learning, build a Jupyter notebook by using Amazon SageMaker, outline the process for evaluating data, explain why data needs to be pre-processed, use open source tools to examine and pre-process data, use Amazon SageMaker to train and host a machine learning model, use cross-validation to test the performance of an ML model, use a hosted model for inference, and create an Amazon SageMaker Hyperparameter tuning job to optimize a model's effectiveness. That concludes this module. Thanks for watching. We'll see you again in the next video. Hi, and welcome to Module 4 of AWS Academy Machine Learning. In this module, we're going to look at forecasting. We'll start with an introduction to forecasting and look at how time series data is different from other kinds of data. Then, we're going to look at Amazon Forecast, a service that helps you simplify building forecasts. At the end of this module, you'll be able to describe the business problem solved with Amazon Forecast, describe the challenges of working with time series data, list the steps required to create a forecast by using Amazon Forecast, and use Amazon Forecast to make a prediction. See you in the next video. Hi, and welcome to Section 1. We'll get started by reviewing what forecasting is and some use cases for it. Forecasting is an important area of machine learning. It's important because there are so many opportunities for predicting future outcomes based on historical data. Many of these opportunities involve a time component. However, while the time component adds additional information, it also makes time series problems more difficult to handle compared to other types of predictions. You can think of time series data as falling into 2 broad categories. The first type is univariate data, which means there's just one variable. The second one is multivariate data, which means there's more than one variable. There are several common patterns in time series data. The first pattern is a trend. With a trend, you get a pattern with the values increasing, decreasing, or staying the same over time. There are seasonal patterns. These reflect times of the year, month, day, or other patterns. Cyclical patterns are similar to seasonal patterns. These are patterns that repeat, like a large retail sale event that happens the same time each year. Finally, there are changes in the data over time that appear to be random or that have no discernible pattern. There are many uses for forecasting. You can use forecasting in marketing applications, such as for sales forecasting or demand projections. It could also be used in inventory management systems that anticipate required inventory levels. Forecasting energy consumption can help predict when and where energy is needed. And weather forecasting systems can be used for governments and commercial applications, such as agriculture. That's it for this section.